In this video, I'm going to look at logistic regression. So in the last few videos, we've been looking at simple linear regression, but logistic regression is used if we have a response variable that's binary, so meaning it can take one of two values. So to illustrate, we have this data set here on guppy mortality. So this is an experiment where 160 guppies were exposed to treatments of either 3, 8, 12 or 18 minutes of exposure to a temperature of 5 degrees Celsius. And then the outcome was whether the guppy survived or died. And so this mortality variable here is equal to 1 if the guppy died and 0 if the guppy survived. We can summarize the data in this table here. So mortality 0 means the guppy survived, mortality 1 means the guppy died, and I think we can see that the longer the fish are exposed to the cold temperature, the more chance they have of dying, which is not surprising. We can also graph the data. So one thing with using a scatter plot when you have a binary response variable is that because the response variable can either be 0 or 1, when we create a scatter plot with that variable, there's a lot of overplotting, and so it's actually hard to see all the data points. And so what's been done here is that the data have been what's called jittered. So this word here, jitter, and that means it's just been shifted by a random amount to give us a better chance of seeing all the individual data points. In this case, the predictor variable also happens to have just one of 4 discrete values, so it's been jittered in the horizontal direction as well. There's no requirement for a logistic regression model to have a discrete predictor variable. It can work just as well with a continuous predictor variable. So even with the jittering, it's a little hard to see what's going on. We can see that for 3 minutes of exposure, most of the guppies survived. So mortality equals 0 is the surviving ones, and then there was just a handful of guppies that died at that length of duration of exposure. Whereas when we increase up to 8 minutes exposure, we've got more dying than surviving. The next treatment level, 12 minutes of exposure, we've got a lot more dying than surviving, and then the longest duration of exposure, 18 minutes, almost all of the guppies in that treatment group died, and only 2 survived. So we're going to fit a logistic regression model here, and one way of thinking about the logistic regression model is it fits a curve to the relationship between the response variable and the predictor variable. So it's doing a very similar thing to linear regression, only instead of working with a straight line, it fits a curve instead. And it's a particular type of curve that's given by the mathematical logistic function. And the way that we fit one of these models is, instead of using LM here, we use GLM. So we can see what GLM is doing. So GLM stands for Generalized Linear Model, and you can read all the details in the help function here. If by mistake we were to try and fit a linear regression model here and just use LM, we would get a regression equation representing a straight line. So there would be a straight line here instead of this curved line, but that resulting linear regression model would not satisfy the assumptions of a linear regression model. And so even though it's possible to fit a linear regression model to data like this, the results are meaningless because the resulting model does not satisfy the assumptions. And so that's one reason why we need to use a different type of model in this circumstance, and the type of model that we're going to focus on here is the logistic regression model. So just to repeat that point because it's important, if we have a binary response variable, we cannot fit a linear regression model to that type of data. Instead, we need to fit a logistic regression model and use GLM here instead of LM. Generalized linear models is a whole class of models, and there's lots of different types of generalized linear models. And so to specify a logistic regression model, we have to set this argument here, the family. And if we write binomial here and then parentheses link equals logit, close parentheses, then that's what R understands to be a logistic regression model. So let's fit that model and then summarize it. So a lot of the output is very similar to when we fit a linear regression model. So we can see that there's an estimated intercept term and an estimated regression parameter for the predictor variable. So I'm not really going to call this a slope here because it's not a slope because we don't have a straight line anymore. So we're going to think of this as the regression parameter that multiplies the predictor variable. And then we can put these two estimates into the fitted logistic regression equation, and that enables us to make predictions. So for example, let's suppose I wanted to predict the probability of a fish dying when the duration of exposure is 10 minutes. So we can think of this curve here as tracing out the fitted probabilities of dying as the duration of exposure increases. So when the duration of exposure is quite low, so 3 minutes, then the probability of dying according to this fitted logistic regression curve is just a little bit over 0.25. As we increase the exposure time, that probability increases, and then at an exposure of 10 minutes, if we trace across to the vertical axis, it looks like we get a predicted probability of dying as being about, what is that, 0.6, 0.7. I'm thinking it's just a little bit above 0.6. And then as we increase the exposure further, we increase the probability of dying until at 18 minutes we're almost at a probability of 1. We're not quite there. It's not certain that the fish will die, because after all we had 2 survivors who were exposed for that length of time to the cold temperature. So it's not 1 by this point, but it's up there. It's 0.9 something, I think. So how do we actually get those probabilities? So we can do it longhand and actually use the logistic regression equation and calculate it all by hand, but it's much easier to just use the predict function. So if we were to look at the predict function, if I can spell it correctly, predict, and then you can see that there's lots of different types of predict function, and the one we want is predict.glm. So that tells us all about predicting from a fitted generalized linear model. And so in particular we need to specify the type of prediction, and then we need to set up the data frame so that we can specify the value of the predictor at which we're going to make the prediction. So in this case, if I set type equal to link, and then set up my new data to be an exposure duration of 10 minutes, then I get what is known as the log odds. So the log odds of dying at x equals 10 is equal to 0.736 3054. But that's not quite what I wanted to do. What I wanted to do was I wanted a probability. So to get the probability, I have to transform this number here, and one formula for that transformation is given here. So it gives me a probability of 0.676. Another formula for calculating the probability from a log odds is given here. It's a little bit easier. It gives me the same answer either way. So that's one way of getting a predicted probability, is to first calculate the log odds and then transform the log odds into a probability. So it's a little bit cumbersome doing it that way because there's 2 steps. These formulas are a little bit cumbersome, so it's actually easier to use this predict function and set type equal to response instead of what we set it to before was link. And so you have to remember to do this because the default setting for type is link. So if you forget to set type manually, you'll end up with a predicted log odds rather than a predicted probability. But if you set type equal to response, you'll get a predicted probability directly. So just to show you that, we're getting the same number that we got before. So looking back at my graph, what this is telling us is that at an exposure time of 10 minutes, the value on the vertical axis is 0.676. So a probability that a guppy exposed for 10 minutes to a temperature of 5 degrees Celsius, the probability that they're going to die is 0.676. A value that is quite commonly calculated in this type of analysis is something called the LD50, standing for lethal dose 50. And so what this is we're thinking of a probability of death of 0.5, and we're finding out which exposure time would correspond to that predicted probability. So we're kind of reversing what we did just now, where we started with a value on the x-axis and figured out what the value on the y-axis was. This time we're starting with a value on that y-axis and figuring out what the corresponding value on the x-axis is. So just kind of eyeballing the graph, if I trace across from 0.5 and then down to the horizontal axis, I'm getting an exposure duration of about 7. It looks like 7 minutes. So at 7 minutes, half the fish are dying on average. To calculate that, this is the formula for calculating the lethal dose 50. So we're taking this number and then dividing it by this number and then taking the negative of that. So to do that, we're using this code here. So the negative of the estimated intercept divided by the estimated regression parameter for the predictor variable, and that gives us the LD50. So the LD50 it's about almost 7 minutes, 6.93 minutes. So that lines up with what we were eyeballing from the graph here. We can check that we've calculated it correctly by figuring out the predicted probability for the LD50, and of course, because of the definition of the LD50, it ought to be 0.5. So this is a good check that you've got the correct answer for the LD50. You should just plug it back into the prediction equation and we should get 0.5. Okay, the last thing I want to talk about here is to think about the significance of the regression parameter that multiplies the predictor variable. So this is the number in the model that tells us whether we've actually discovered a relationship between mortality and duration of exposure in this instance. So to figure out whether we've established a regression relationship between the response variable and the predictor variable, the regression parameter here is what tells us whether there is a relationship there or not. If this number was 0, that would mean there's no relationship. Again, we've got the usual statistical inference idea that this is a sample estimate. What we really want to do is do a hypothesis test for the parameter in the population. And so it's tempting to look over here in this table and go, oh, there's a test statistic, there's a p-value. I'll just use those numbers. These are known as the walled test statistic and the p-value for the walled test. And I wouldn't rely on these. There's some inaccuracy involved in these numbers, and so there's actually a better way of doing this test. So we're not going to do the walled test for this. Instead, we're going to look at something called the analysis of deviance table. So this is analogous to the analysis of variance table in linear regression, and so that's why we obtain it using the ANOVA function. And we can see here that there's this quantity here called the deviance, and this is the test statistic that we're going to use. So we're doing a hypothesis test here, so I'm going to lay out the 4 steps. So step 1 is to state the null and the alternative hypotheses. So the null hypothesis is that the regression parameter that multiplies the predictor variable is at 0 in the population, versus the alternative hypothesis that that regression parameter is not equal to 0. Second step, find the test statistic. So it's given by the deviance in this analysis of deviance table. Third step is to find the p-value for that test statistic. So it's given here in this column of the table. So this is coming from a chi-square distribution with 1 degree of freedom, and it's 2.12 times 10 to the minus 11. Really, really tiny number, essentially 0. And then step 4, make a decision, draw a conclusion. So we're going to reject the null hypothesis in favor of the alternative hypothesis because this p-value is smaller than our significance level 0.05. So we're going to conclude that the regression parameter multiplying the predictor variable is not equal to 0. So in other words, we have established a relationship between the response variable and the predictor variable. In particular, we could say that the duration of cold exposure does affect the probability of guppy mortality. So that's an introduction to logistic regression models. There's a lot more we could say about logistic regression models, but we're just kind of touching on this type of model in this course. And so everything we've covered in this video, these are all the highlights, the things that you need to know for the purposes of this course.